Remember for 8.2, the first thing we know is when there is an eigenvalue and an eigenvector, they're all distinct and there's n of them. You're done, it's easy, piece of cake. Right? That was this example right here. 2 by 2 system, 2 eigenvalues, 2 eigenvectors. Your solution is immediately known. Easy peasy. When you have repeated eigenvalues, if your number of eigenvectors equals your multiplicity, you're done, easy peasy, write down the solution. It's exactly the same as the previous case. Okay? But it's possible to get a case where your eigenvalue is repeated. So when you solve for your eigenvalue, and we're taking advantage of technology to actually do these for us in this class. You can do them by hand like we learned back in linear algebra, but once you find your roots to your characteristic polynomial, your eigenvalue, if it has multiplicity m, and you only have one eigenvector that goes with it, then you have to build m linearly independent solutions. Now what we did in class was this simple case of that option. Right here was the example. So we got a lambda equals -3 and a single eigenvector to go with it. All right, so we know the first solution looks like this, right? In fact, maybe I'll scroll up here to this box. The first solution is exactly what you'd expect it to be. Eigenvector times e to the eigenvalue t. That solves the linear system. This linear system, x prime equals ax. x2 now is going to be your eigenvector t e to the lambda 1t. Notice how I put a t in there. Plus some new vector v2 e to the lambda 1t. You see the pattern? I stuck a t in here, and now I just have the eigenvector v2, which we don't have an eigenvector v2. So where do we find it? We get it from what's called a generalized eigenvector, which is the solution to this equation right here. So remember that v1 is the solution to this equation. A minus lambda I v1 equals 0. It's the eigenvector is the solution to this. And then what I do to find the next generalized eigenvector is use the same equation, a minus lambda 1 I v2 equals v1. Okay? And that's what we did in this example right here, is we found v1, then we set a minus lambda I times v2, the unknown, equal to the v1 that I got as my eigenvector. And then I solved that for any solution. Any one solution will work. There's going to be infinitely many, and they're infinitely many because a minus lambda I has a determinant of 0. It has a determinant of 0 because that's how we found lambda in the first place. Is we set the determinant of a minus lambda I equal to 0 and solve for lambda. When the determinant is 0, that means there are infinitely many solutions, or there's no solution. In this case, there will be a solution to this equation. Okay, so we solved it. We got this 0, -1, 6. Actually, what we did was we just took one of these equations, which cancel each other out because they're basically the same equation, and we picked one value for A and solved for B, and we got the number. We could pick a different solution and it still would work. And so then my x2 is v1 t e to the lambda t plus v2 that I just found e to the lambda t. Okay. So the last thing I wanted to do is take this one size higher. Let's do this with n equals 3. Actually, I want to generalize it. Do I have? Yeah, let's do a 3 by 3, and then I'll write down the general form of this thing. And then the last thing we got to do in 8.2 is complex eigenvalues and eigenvectors. Okay, so let's say.
Just broadcast.
Absolutely. Yes, I am recording, I'm just not broadcasting now that I've done all my review. X prime is equal to 2, 1, 6, 0, 2, 5, 0, 0, 2 times x. There is your first order system. You got 3 dependent variables, like whatever x is, if it was like x, y, z. Now this system is basically saying that x prime is 2x plus y plus 6z. Y prime is 2y plus 5z. And z prime is 2z. Okay, so here's how we solve these. First thing we do is we find the eigenvalues of 2, 1, 6, 0, 2, 5, 0, 0, 2. If I do that in Maple or in, well, this is the notation for Wolfram Alpha. I've given you the notation for Maple, but if I do that, I get lambda 1 is 2, and V1 is 1, 0, 0. And in fact, I get lambda 2 is 2, lambda 3 is 2. So this has multiplicity 3 and only one eigenvector. So here's what I do. My x1 will be equal to v1 e to the lambda 1t, which is 1, 0, 0 e to the 2t. I'll go ahead and just because I want you to see it, I'm going to make sure in Wolfram Alpha you see what it looks like when we get the repeated eigenvalue with only one eigenvector. I think you've seen it before, but if I do eigenvalues 2, 1, 6, comma, 0, comma 2, comma 5, comma 0, comma 0, comma 2, 2, 2, 2. Your V1 is 1, 0, 0, but when they're V2 and V3 are 0, 0, 0, that means they're not eigenvectors. They'll be non-zero. Okay? All right, so then there's your x1. Your x2 will be V1 t e to the lambda 1t plus V2 e to the lambda 1t, where a minus lambda 1I times your unknown V2 is equal to V1. You solve this. Okay? But the good news is Wolfram Alpha gave this to me. It actually already solved this for me and came up with something called a generalized eigenvector. So if I go back here, look at U is 0, 1, 0. This corresponding generalized eigenvector. So V2 turns out to be 0, 1, 0.
What does that mean?
Generalized eigenvector? Well, it means one of two things, depending on what context you bring this into your courses. In this class, it just means it's the solution to this guy. So like the eigenvectors are solutions to this. Hold on. V1 equals 0. Anything that solves this is an eigenvector. If you get the V1 and you plug it in here and then solve this, that's a generalized eigenvector. When we talk about them in linear algebra, which we didn't get to in our class, you usually don't get to them in a first semester of linear algebra. You might get to them in graduate linear algebra, or if we had 2 semesters of it. The other way to define them is as A minus lambda 1I, where again lambda 1 is the eigenvalue, but it's any power of that times some V, we'll call it K, equals 0. These are generalized eigenvectors. Wolfram alpha. So anything that solves this for a given K bigger than 1 is called a generalized eigenvector. Whereas when K is 1, it's just regular old eigenvectors, right? So it turns out this is equivalent to saying what I said down here, but again, the whole benefit now is Wolfram alpha is giving you the generalized eigenvector, which is the solution to this, which means it goes right there. Yes, sir. We are. I'm not done yet. Yes. So it's coming next. There have to be 3 of them because it's a 3 by 3 system. And so what I'm going to do to get the third one is go back up here to this formula when I introduce this case. And I'm going to look at one like this. And now the third one on the list is going to be the second generalized eigenvector, or the third vector that's been returned to me by Wolfram alpha. So I'm up to x2 now. Oh, come back down here. So plug it in. I've got 1, 0, 0. This is just this one right here. T e to the 2t plus 0, 1, 0 e to the 2t. This one has a t in it. This one doesn't. So this turns out to be a solution. In fact, we derived why this was a solution back in the simple 2 by 2 case that I gave you, the example that I gave you. You could again plug this in and verify that it's the solution to this that makes this vector here the right vector, so that this solves the x prime equals ax equation. Now x3 is going to be v1 t squared over 2 factorial, which is just 2, e to the lambda 1t, plus v2 t e to the lambda 1t, plus v3 e to the lambda 1t. Do you see the pattern of how these are expanding? I'm inserting a t to the m over m factorial inside here. And then e to the lambda 1t. And now I've got a new vector 3. And again, if I were to plug all of this into the system up here and solve for v3, what does v3 have to be? It has to be the solution to where a minus lambda 1I of v times v3 equals v2. So notice how the v1 shows up here, and now the v2 shows up here. And if you kept going, if you had a 4 by 4, the next one would be one term longer for your x4, and then you'd have a minus lambda I v4 equals v3. And now we know what v3 is, so then you'd solve for v4. In this case, we're only at 3, so we stop here. And again, from Wolfram alpha, we get that v3 is 0, negative 6/5, and 1/5. Again, keep in mind that this v3 is only one of the infinitely many solutions to this, but it's the one that one is sufficient. We just need a single one. So x3 is now 1, 0, 0, t squared over 2, e to the 2t, plus 0, 1, 0, t e to the 2t, plus 0, negative 6 fifths, 1/5 e to the 2t. So now you have 1, 2, 3 linearly independent solutions to your original system. Which is, it's pretty significant how simple this is to come up with a solution. Relative, assuming that you can find eigenvalues and eigenvectors, and that you can find generalized eigenvectors, once you know that, writing down these solutions is immediate. Which, by the way, is a whole lot better than that giant, nasty elimination method that I taught you back at the end of chapter 4. Now, what is the final solution? What's the general solution?
Isn't it a set?
It's a family of solutions. So in that sense, yes, it's a set. But it means you plug in C1, C2, C3. It's a 3-parameter family of solutions, but now your x1 was this first guy, your x2 was this guy, and your x3 is this one. Okay?
Sounds like one fit on one line.
And it depends on how tightly you can combine things. C1, 1, 0, 0, e to the 2t, plus C2, 1, 0, 0, t e to the 2t, plus 0, 1, 0, e to the 2t, plus C3, 1, 0, 0, t squared over 2, e to the 2t, plus 0, 1, 0, t e to the 2t, plus 0, negative 6 fifths, 1/5, e to the 2t. There's one form of your solutions. Or you can take this one step further and write this in terms of x1 of t, x2 of t, x3 of t. Right? Because this is x1, x2, x3 equals this whole thing. Right? So let's just multiply in my constants and my functions and then just add them up. Notice how, when I multiply into this one, I only get a C1 e to the 2t up here. Nothing down here. On this one, I get a C2 t e to the 2t, and then nothing from this one. And I get a plus C3 t squared over 2 e to the 2t from here, and then 0, 0. So that's what my x1 function looks like. It's a C1 e to the 2t plus C2 t e to the 2t plus C3 t squared over 2 e to the 2t. All right, what does x2 have in it?
Just
From right here,
e to the 2t plus
and don't forget this C2.
C2 e to the 2t plus C3 t e to the 2t.
And this one here,
Oh, okay.
minus, you could do it like this, 6 fifths e to the 2t.
Oh, okay.
Because the C3 is times this whole thing. And the only place where x3 comes into play is the last one. So it's C3 times 1/5 e to the 2t. Actually, I think that's sufficient. I'm not going to write down the case 2 in general. I think we've got the right idea. That you just keep adding additional terms to your next x sub I, your capital X sub I. You add that additional term, but at the end, I mean, you put your eigenvector, your previous generalized eigenvector, and then that last generalized eigenvector. Okay.
So when we're using Wolfenhausen, but we can just pretty much skip all of it.
You go straight to the end. I mean, all I've done is write out x1, x2, x3 separately. I spent a lot of time talking, but I really didn't do anything, right? All I did was plug this in, get these numbers, write down my solutions, which I could have written it down right here immediately. So yes. That's why linear systems are so fantastic. Once you can, if you can write it in as a linear system, homogeneous, boom. Now, when it's non-homogeneous, again, I'll refer to this next time, that's when you've got to basically extend our techniques for method of undetermined coefficients and variation of parameters. Essentially, we always do variation of parameters. That's the right choice for us in general. But to get a homogeneous solution, this is what you do when there's no forcing term. Which is also the reason why the first thing you do when you have a nonlinear system is linearize it, which means near points of interest you find what's the closest linear system to that nonlinear system, and by that you can explore things like the stability of that point. Is it stable? Is it not stable? I haven't decided how much detail I'm going to go into that, but from these eigenvalues and eigenvectors, you can draw what are called phase portraits, so you can see how is the solution behaving near certain points. Is it collapsing? Is it a sinkhole? Or is it a repellent where everything near that goes away? Does it asymptotically approach lines? You see a lot of interesting behaviors when you start graphing these eigenvectors on the phase portrait and look at the what are called the equilibrium solutions. All right, last thing we need to do then is, what about the complex case? Complex eigenvalues and eigenvectors. All right, so example. dx dt is 6x minus 7y, and dy dt is equal to 5x plus 4y. So I'm going to do eigenvalues of 6 and negative 7 and 5, 4. Six comma negative 7. 5 comma 4. Not negative 7, negative 1. I don't know where I got that 7. Did I write 7? I don't want a 7. Take the 7 off and just make it negative 1. I want some neater ones to start with. Although we could do it, it'll be better for our first example to not be so nasty. So take that off. Just make it 6x minus y. So this is a 1 here. Boom, boom. And I got lambda is 5 plus 2i, that's lambda 1, and v1 was 1/5 plus 2/5 I 1. Double check that. Lambda 1 is 5 plus 2i, and 1/5 plus 2/5 I 1. And lambda 2 is 5 minus 2i. V2 is 1/5 minus 2/5 I 1. Just, again, a refresher, it's perfectly legitimate for us to get complex eigenvalues because we're solving a polynomial. We're solving a quadratic equation. In this case, our characteristic polynomial turns out to be 6 minus lambda times 4 minus lambda plus 5 equals 0. Right? That's the characteristic polynomial, right? You take lambdas minus diagonal and do forward minus back. So when you solve this, that's where we're going to end up with 5 plus or minus 2i as the solution. I'm not going to go through writing it out, but that's what you get. And then when we plug those back in and solve for our eigenvectors, we can find these eigenvectors right here. The question is now, what do we do with those? Now, of course, we can use the very first case we talked about and say, aha, this is x equals c1 1 over 5 plus 2 over 5i 1 e to the 5 plus 2i t plus c2 1/5 minus 2/5 I 1 e to the 5 minus 2i t. That is a true statement, but we don't like it. What do we not like about it?
It's got eyes in it.
It's a real world problem with real coefficients, and now my solution function has i's in it. Now, just because a function has i's in it does not necessarily mean it's a complex valued function. It's possible to have i's in it and it still be a real valued function, meaning that every time I plug in a t, my output still turns out to be only real and have no imaginary parts. That the imaginary parts cancel themselves out. In fact, with right choices of C, I can convert this into a purely real function. Now, we did that way back in, I'm guessing, 4.3. We did some stuff. Right, where was it? I derived it. This whole section right here. This is from 4.3. I used Euler's formula to convert these e to the I things into sines and cosines. Then I took a good choice of how to combine these together so that the i's dropped out. And basically what I was able to show is that the general solution with the i's in it was equivalent to a general solution without i's. I walked through that whole process with you. I'm not going to read through it again. I'm not going to go through it again. I'm just going to point out the fact that because what we're really finding are linearly independent solutions, and any combination of those solutions is still a solution, you just take good choices for how to combine them and add them together so the i's drop out. The point is, we can do that, and we can also do that in this case. Dot, dot, dot. Using similar arguments as in 4.3. And just for the sake of time, I'm not going to go through it in detail. He actually does it in the book, so if you wanted to read the ebook, go for it. I know that's something that's high on your list in terms of what you need to get done before the end of the semester. If not, then trust me, I never say trust me without the caveat of the real information out there of why you should trust me is available to you, and you can go read it if you need to. That I can rewrite this in terms of two solutions. X1 is, and let me write it down and see if you can see where the pieces are coming from. 1/5 1 cosine of 2t minus a 2/5 and a 0. That's not to the 2t.
I was like, what is that?
That's a good question.
That's not
It's
funny.
of 2t, sine of 2t, all times e to the 5t. And then x2 is 2/5 0 cosine of 2t plus 1/5 1 sine of 2t e to the 5t. Okay, so again, what I would do if I were going to write this all out is I would split the e's and use Euler's formula for the ones that have i's in it, and then I'd choose good C1s and C2s to show that both of these, x1 and x2, are solutions. For good choices of C1 and C2, I can get to x1, and another good choice for C1 and C2, I can get to x2. And notice how there are no i's. Yeah. That's the beauty. These are also, I'm not going to prove it here, but they're linearly independent of each other, which means your x general solution would be C1x1 plus C2x2 for any real C1 and C2. Okay? This going here and this going here. All right, now where are the different pieces showing up? Just so you can see some of the pattern here. Notice here's this 5 here. That's this 5 and this 5. Okay? This 1/5 and this 1 is this 1/5 and this 1 and this 1/5 and this 1. This 2/5 and the fact that there's nothing with an I down here is this and this and this and this. And then lastly, the 2 here are the 2's that are right there. Yes, sir. Notice all I really care about is this right here, because these are just the conjugates. Remember the word conjugate? Just change the middle sign. 5 plus 2i, 5 minus 2i. 1/5 plus 2/5 I, 1/5 minus 2/5 I. So I just need one of those to get all the pieces that I need to build this solution. Okay?
Well, where did the zeros come from?
What zeros?
The 2/5 and the matrix. It's in purple.
Oh, because there's no I in the second component.
Okay.
So this right here is like 1 plus 0i, right? And this one right here is like 1 minus 0i.
Does it matter which one you put the negative with?
The negative here matters.
How come you put it with x1 when it was the v2?
It has to do with the fact that the vector times the cosine is the real part, and the sine of t is the imaginary part.
So how come x1 got the...
I mean, it doesn't matter. I could call this x2 and this x1.
So that's what I was asking. So it doesn't matter which one you put it with?
Yeah. I mean, I have two different linearly independent solutions, and it doesn't matter which one's which. So the point is, in the ... section right here, I would choose a certain C1 and a C2, and I could get one of these, and if I choose a different C1 and C2, I could get another one of these. That is, I can turn this X into either one of these with a right choice of C1 and C2, which makes it a solution. As long as, I mean, this is the general solution, but I can get to things that don't have I's in it. All right, so let me write down just the theorem so you know how to do this in general. All right, theorem 8.2.3. These are real solutions corresponding to complex eigenvalues. All right, let's let lambda equal alpha plus beta I be a complex eigenvalue of A in the system x prime equals A x. It's the homogeneous system. Let's let K, no, actually, let's use V. V be the corresponding eigenvector. And for the record, I'm keeping things simple by not talking about what happens when you have repeated complex eigenvalues. It's basically a similar approach to what we did before. You have to combine. I mean, these things can get very, very messy for larger numbers of n, for multiplicity, some complex, some not. These are all the building blocks that you need to build some of those more complicated systems. I'm not going to do anything that crazy. All I want is, let's say we've got a single complex conjugate eigenvector and eigenvalue. We know that their conjugates are also eigenvalues and eigenvectors. So let's just say we got lambda and v goes with it. Now v may have i's in it. So what I'm going to do is I'm going to set, I'm going to call it b1 equal to the real part of v, the eigenvector. Okay, that means the real part. The things without the i's. So like that 1/5 and 1 that I had up here in my example. And I'm going to let B2 be the imaginary part. If you need a refresher, if you have A plus BI, remember that A is the real part. If that's Z, that's the real part of Z, and B is the imaginary part of Z. Remember that this has no I in it. It's the coefficient of the I. So when I say imaginary part, I mean I'm stripping off the I and just taking the things that have I's. That's why the purple up here was 2/5 and 0. That's the imaginary part of the eigenvector. The blue is the real part of that eigenvector. Does everybody see that, what I'm talking about? Mm-hmm. Okay. So then the solution, or I should say then x1 and x2, I'm going to write them both, are the two elements of the fundamental set of solutions. They're the linearly independent solutions that you can combine to get the general. Looks like this. B1 cosine of beta t minus B2 sine of beta t e to the alpha t. It's exactly what this right up here looked like. It was the real part cosine of the imaginary part of your eigenvalue t minus the imaginary part, sine of beta t, e to the alpha t. Just shrink it so I get it all on one page. Right, there's your alpha plus beta I. So there's your alpha, there's your beta. And then the other one would, of course, be, you switch these b2 cosine beta t plus b1 sine beta t e to the alpha t. Are linearly independent solutions. To x prime equal ax. And the proof of this, I've really talked you through the proof of it without telling you what the C1 and C2 are that I would use. But this up here, right, this answer comes from the very first theorem in the section. That we know that this is a general solution to that 2x2 system. And then that these are also solutions just means, can I find a good C1 and C2 that gives me this one? And can I find a C1 and C2 that gives me this one? And then show they're linearly independent. And there you've got a proof. So I'm not actually going to write out the proof. What I am going to do is one more example. Let you guys type it into Maple and see if you, or into Wolfram Alpha, see if you can't come up with what the solution looks like. So let me write it down first, and then I'll release your computers. In fact, I'll even do the typing it into Wolfram Alpha up on the screen if you haven't logged into your computer and don't have your browser open. But either way, you can do it yourself in practice, or you can watch me. 2, 8, -1, -2. And by the way, let me just do one, since I've got a little bit of time here. I think I can finish this. Let's kick it up one notch and make it an initial value problem. Right? As an initial value problem, that means we're actually going to find a specific solution.
Was that 2, 1, or
2,
two?
-1. No, 2, yeah, 2, -1. That's what I wanted. 2, -1. Two comma 8 negative. Can't type for some reason on this one. -1 comma -2. We'll pause. So your alpha and your beta are 0 and 2. Your real part, B1, is -2, 1. Your imaginary part is -2, 0. I don't know why, but I often accidentally include that 1 right here. I have to catch myself. -2, 0. So what I'm going to do is, in writing my answer, instead of writing x1 out and x2 out, and then write x as c1, x1 plus c2, x2, I'm going to do it all together. So c1, now x1 is -2, 1 cosine of 2t, -2, 0 sine of 2t. And then there's e to the 0t because of alpha. So plus C2. Now I'm going to take B2, which is,
Isn't it sine and cosine of negative 2t? Isn't beta negative 2?
since I use this V, I'm using positive 2 here. Right, there was a lambda equals 2i and a lambda equals negative 2i. I mean, you could use this one, but you just have to make sure that your real part and imaginary part came from this vector that goes with this one.
So we just pick either one to come up with both of these solutions?
Yeah, just pick one pair. So I didn't even need this pair to do this. I'm just going to use one.
That's what I was.
Yeah. So negative 2, 0, cosine of 2t plus negative 2, 1, sine of 2t times e to the 0t. What I would go ahead and do, simplify this a little bit because of the zeros in here, I would write this as C1 and then times its vector. Let's multiply these in and combine them. So I get like a negative 2 cosine of 2t minus a minus makes plus 2 sine of 2t. And then down here on the bottom one, I just get cosine of 2t. That's all of that. I'll go ahead and broadcast so you can see it up close if you need to. And then I would do C2 times, this one's going to be negative 2 cosine of 2t minus 2 sine of 2t, and then sine of 2t down here. And I could have gone ahead and put the C1, C2 in there and write this as one vector. Doesn't really matter. This is just the way that I've typically done it. Make sense? So that's the general solution. What do we got to do now? Initial conditions, right? Use x at 0, that is plugging in t equals 0, and set that equal to 2, negative 1 to find the specific solution. So x at 0, if I just plug in 0 all the way through here, I get C1 times, the cosines of zeros are all 1, the sines of zeros are all 0. So negative 2, 1. Equals 2, negative 1. So I have negative 2c1 minus 2c2 equals 2, and c1 plus 0 c2 equals negative 1. So clearly C1 is negative 1, which means that negative 2 times negative 1 minus 2C2 is equal to 2. Just plug that in there. 2 minus 2C2 equals 2. C2 is 0. So my solution is a negative 1 times negative 2 cosine of 2t plus 2 sine of 2t cosine of 2t, or 2 cosine 2t minus 2 sine 2t and a negative cosine of 2t. Right. the first is my x1 or x, and the next one is my y or my x2. I'm going to stop there, but what I will come back and do at the beginning of class on Tuesday is I want to tackle a couple of questions. One, what kind of systems, like real world things, show up as these homogeneous systems? And then I want to look at the graphs of some of these solutions. Because you're graphing a couple of different things when you want to visualize what's happening here. Typically, you'll be thinking of X like as the population of wolves, and Y as the population of rabbits, or something like that, right? Or you could be doing what's called an SIR model, the epidemiological studies where you've got people spreading disease or illness. You've got the susceptible, you've got the ill, and you've got the recovered. And so you've got a 3x3 system where you're modeling those three types of populations and how they interact with each other. So a lot of times what you'll do is just graph them independently. So you graph the x1 function, the x2 function, the x3 function, all with respect to time on a single graph. But sometimes it's interesting to also look at what's called a phase portrait, where you graph this right here as a parametric equation. Sorry, forgot to turn my noises off. So we'll do that next time. You do have homework, basically doing what we've done in the last several examples of find the eigenvalues, eigenvectors, write me the solutions. Okay? With Wolfram Alpha handy.
The extra credit that you gave us for the first session was supposed to be like a free homework.
It's a free drop. I have not included that yet.
Are you dropping one of our homework?
Yes. I do drop. By this is my standard practice. It doesn't say this in the syllabus, but I drop 2 homework assignments, the lowest 2 anyway. And I always wait till the end to tell you guys that on purpose.
So it's going to be plus the one that you earned?
If you earn 1 extra, you get that one. And if you went to the second one, you get a free 100.
Darn, don't drop my 96 of it.
We'll drop that one. It won't hurt you. Do what?
It was 3.2. But, so,
Can you 8?
yeah, I saw 8.2 is good.